Torchheaviside. Description: the torchheaviside function implements the heaviside step function, which returns 1 for values greater than or equal to 0 and 0 for values less than 0. It is a useful function for various applications, particularly in signal processing and machine learning. Inputs. Input: the input tensor for which the heaviside function is applied. This input tensor can be of any numerical data type, e.g. float, double, int. Values: an optional tensor that specifies the value to return for elements of the input tensor that are equal to 0. If not provided, the default value for elements equal to 0 is 0. The values tensor should have the same shape as the input tensor or be a scalar. Outputs. Output: a tensor with the same shape as the input tensor containing the results of the heaviside function. For each element in the input tensor, the output tensor will contain 1 if the element is greater than or equal to 0 and 0 otherwise. Steps. Element-wise evaluation for each element in the input tensor. The heaviside function is applied. Value assignment: if the element is greater than or equal to 0, the corresponding element in the output tensor is assigned the value 1. 0 value handling: if the element is equal to 0 and the values tensor is provided, the corresponding element in the output tensor is assigned the value specified in the values tensor. Otherwise, it is assigned the value 0. Challenges and fixes. Challenge 1: unexpected behavior for elements equal to 0 when the values tensor is not provided. Sample use case that resulted in challenge 1 when applying the heaviside function to a tensor containing elements equal to 0 without specifying the values tensor. The output tensor might not have the expected values. Fixes to challenge 1: provide the values tensor to specify the desired value for elements equal to 0. If the desired value is not 0, explicitly pass the desired value in the values tensor. Challenge 2: mismatched shapes between input and values tensors. Sample use case that resulted in challenge 2: providing a values tensor with a shape different from the input tensor can lead to an error. Fixes to challenge 2: ensure that the shape of the values tensor matches the shape of the input tensor or that it is a scalar. If the values tensor is a scalar, its value will be broadcasted to match the shape of the input tensor. Torch adjoint. Description: the torch adjoint function calculates the adjoint of a given tensor. Adjoint is a generalization of the transpose for complex valued tensors and matrices. It involves taking the transpose of the tensor and then taking the complex conjugate of each element. Inputs. Input 1 tensor: the input tensor for which the adjoint is calculated. It can be a real or complex valued tensor. Outputs. Output 1 adjoint tensor: the resulting adjoint tensor. The adjoint tensor has the same dimensions as the input tensor but with its elements transposed and complex conjugated. Steps. Step 1: the function first transposes the input tensor. Step 2: it then conjugates each element of the transposed tensor, resulting in the adjoint tensor. Challenges and fixes. Challenge 1: incorrect usage for real-valued tensors. Sample use case that resulted in challenge 1: if the input tensor is real-valued. Using torch adjoint might seem unnecessary since it's equivalent to the transpose. However, it might lead to unexpected results if used in complex operations where the real and imaginary parts are treated separately. Fixes to challenge 1: use torch transpose directly for real-valued tensors. Torch transpose is more efficient and avoids unnecessary complex operations. Challenge 2, handling of higher dimensional tensors when dealing with tensors of higher dimensions. Understanding the order of transposition can be crucial. Sample use case that resulted in challenge 2: if the input tensor is a 3D tensor, transposing it using torch adjoint might lead to an unexpected dimension order if not explicitly specified using the torch transpose function with appropriate dimensions. Fixes to challenge 2: specify the dimensions for transposition explicitly using the torch transpose function to control the order of the dimensions in the transposed tensor. Torch array. Description. The torch array function is used to find the indices of elements in a tensor that satisfy a given condition. It returns a tensor containing the indices of the non-zero elements. Inputs. Input 1 tensor, a p-torch tensor. Outputs. Output 1 tensor, a tensor containing the indices of the non-zero elements in the input tensor. The shape of the output tensor is num non-zero elements. Input tensor, NDIM. Steps. Step 1: the function iterates over the input tensor. Step 2: for each element in the tensor, it checks if the element is non-zero. Step 3: if the element is non-zero, the function adds its indices to the output tensor. Challenges and fixes. Challenge 1: incorrectly using torch array on a non-Boolean tensor. Sample use case that resulted in challenge 1. Python. Tensor torch, tensor 1, 2, 3. Indices torch array tensor. Fixes to challenge 1. Convert the tensor to a Boolean tensor using a comparison operator before using torch array. For example, to find the indices of elements greater than 1. Python. Tensor torch, tensor 1, 2, 3. Indices torch array tensor 1. Challenge 2: using torch array on a tensor with multiple dimensions. Sample use case that resulted in challenge 2. Python. Tensor torch, tensor 1, 0, 1, 0, 1, 0. Indices torch array tensor. Fixes to challenge 2. The output tensor from torch array will have the shape num non-zero elements. Input tensor, NDIM. To access the indices of a specific dimension, use slicing. For example, to access the indices for the first dimension. Python. Tensor torch, tensor 1, 0, 1, 0, 1, 0. Indices torch array tensor. First dimension indices 0,